We're going to relax the assumption that there are fluid elements. That's the summary of what I just said. So this lecture will be about treating the plasma as comprised of particles and not fluid elements. And the context here is that you can not always, we saw some systems where you cannot always guarantee that the distribution function is Maxwellian perfectly. It's because the mean free path is long compared to a lot of scales that you're interested in. And because of that, you don't know the distribution function of the particles. You can't necessarily use an MHD fluid-like description to describe the fluid elements in which this distribution function lives. So this will lead us to two parts of this lecture. One is just particle dynamics. If you know something about E cross B drifts and grad B drifts and stuff like this, this will be reviewed for you. If you don't, it should be fairly straightforward because it's just very simple F equals ma with a little twist. The second part of the lecture is about a statistical treatment. So, following individual particles, that gets difficult kind of quickly, right? So, like I said over here on this board, there was something called the plasma parameter. It's the number of particles in a Debye sphere. For example, in the intercluster medium of galaxy clusters, it's like 10 to the 29 or some crazy number. So in every single Debye sphere, there's 10 to the 29 particles, say. And you can't do F equals ma for every single one of those in every single Debye sphere in a megaparsec, right? So instead, and for various other reasons I'll get to, you have to develop a statistical treatment, and that's what's going to lead to something called the Vlasov equation, or in the case where there's collisions, the Vlasov-Landau equation, and I'll get to that. So that's the scheme of this lecture. So first, let's just forget that there are that many particles in a plasma and just concentrate on one particle. And before we subject this particle to any fields, let's just set up a coordinate system, which is useful. Right, so suppose there's some magnetic field here. And I've got some particle in the plasma which has been kicked. Maybe it's got some thermal noise in the plasma, so the particles are moving around. And we know that this thing, this particle is going to do something like this, right? And there might be some electric fields in the plasma, and so you just say this particle is going to move because of some Lorentz force. And its position is just going to follow its velocity. It turns out that writing these two equations and solving them is not necessarily the best coordinate system to work with for particle motion. A better coordinate system, say if there's a particle right here with some charge, is to split this particle position into two pieces. So let's see. So here's R, and that's where the particle lies. And we're just going to decompose that into two pieces. One is pointing here. And one is, let's see. I should just color code all these. And one's pointing there. So this thing here is called the guiding center. And that's the center, that's the guiding center. It's the center of, well, it's the center of the circle that the particle's gyrating around. And then this rho is just sort of a Larmor vector. It's something that just sweeps around in a circle, right? So you can decompose the position of a particle into the motion of its guiding center and then the motion of this Larmor vector, which is just executing Larmor motion as it spins around. And why this decomposition is useful is that the motion of this thing is really simple. It's just going in a circle. It's just an oscillator. And then all the interesting physics is going to happen here on how the guiding center moves. Right, so I suppose to be clear, this right, yeah. So if I define some kind of magnetic unit vector, just b hat, this Larmor radius is just minus v cross that divided by the Larmor frequency, the gyro frequency. So that's just going to sweep around in a circle. Good. So let me ask not how r changes, but how big r changes. And that's tautology, right? It's just right there. R dot is just v. It's the particle velocity. It's the rate of change of the particle position. And then I've got an expression here. Well, I want d by dt of this Larmor vector, whose expression is right there. So it's just that. So one can imagine that the motion of the guiding center could be complicated, right? So this is a time derivative taken along that the trajectory of the particle. You know, the direction of the magnetic field might change as the particle moves. The strength of the magnetic field might change as the particle moves, because this is QB over MC. But let's just do the simplest thing, which is just suppose that B is constant. So we're just going to look at a plasma where there's just a constant magnetic field threading the plasma. And we'll also suppose there's an electric field, but that electric field is constant too. And the only reason to do that is just so that this d by dt comes in here. It doesn't hit the B. It doesn't hit this. It just hits this velocity. And it just makes things simple, because this will be v minus, or v plus dv dt. So that's just moving the derivative in. And then I just use this formula down there for how the velocity evolves. And I've got v so that's just writing out the cross products. So this is the v that's there. There's a dv by dt. I'm just taking that from this board, from the Lorentz force. And that's just going in here. There was a q over m in the Lorentz force, and there's a q over m in the Larmor frequency, so these cancel. And then all you're left with is E, which has been crossed into B, and V cross B, which has been further crossed into B again. And you could see just from the second term, there's a C and there's a C, and those are going to cancel. And there's a B and there's a B magnitude, which is going to cancel. And all you're left over with is just V cross B hat cross B hat. And there's a nice vector identity for that. And that all this stuff is just going to give you minus V perp. So it's the component of the velocity which is perpendicular to the magnetic field. And you just pick up a minus sign from the vector identity. So what that means is that you've got this V, and you've taken off the piece which is just the motion across the field. And so all you're left with is just some parallel motion, and then this thing. So this just says the guiding center is moving because of two things. The guiding center moves because the particle streams along the field. That makes sense. Remember, the guiding center doesn't care about the Larmor motion. So it's just, as the particle moves, sweeps along the field, the guiding center just sweeps along with it. And then across the field, the guiding center is going to drift. And this thing right here is called E cross B drift, because it's E cross B. So there's a few comments on this. I'll actually draw how this happens. But before I say anything about this, one of the first things to notice is that there's no mass and there's no charge in this expression. So whether it's an ion or electron, they're all going to drift the same way. Doesn't matter that one's heavier than the other. It doesn't matter that one has positive charge and one has negative charge. Everything drifts the same way. The second comment is that in MHD, I'm about to derive a bunch of other drifts. But in MHD, the only drift that you ever see in the equations is this E cross B drift. And this term is what's responsible for flux freezing. One way of saying this is that from the induction equation, the electric field changes the magnetic field. And this drift ensures that as that magnetic field moves, the particles move with it. So if you have a single flux tube that the particle is confined to gyrate around and that flux tube wiggles, this drift just ensures that that particle stays in that flux tube as it's wiggling. So I hope that makes sense. Yeah.
One question just to remember that if you have a gradient of B in MHD, then you can induce a drift.
A gradient in what?
B.
B, yeah.
So in MHD, you can also find the drift velocities which are related to gradient.
Yeah, so, well, yes and no, right. So his question was, so I'm about to do a bunch of other drifts too. There's something called a grad B drift, which happens when you have gradients in the magnetic field. You can just see from here, I brought this d by dt in, and I didn't attack any of these magnetic field things. If I did, there would be gradients of B involved. And I just made a comment that in MHD, the only thing you see is this. My claim is the grad B drifts and all the other drifts that aren't this, you don't really see them in MHD. They're in there. But in MHD, this is the fastest drift. So you know how you do induction equation? This U here is the E cross B drift. It's not the grad B drift. The grad B drift is actually smaller than the E cross B drift in MHD. I do this in the notes, actually. I take all the other drifts and compare them to the E cross B drift in the MHD ordering, and they're all small. They're still there. Actually, this brings up an important point. Remember I said here, it doesn't depend on charge, it doesn't depend on mass. So where is the current in MHD, right? I mean, if all species are E cross B drifting at the same rate, there's no perpendicular current. But there is a perpendicular current, or else there's no Lorentz force. So it's these additional drifts that give you the perpendicular current, right? So the grad B drift gives you a perpendicular current. But those drifts don't show up here in the induction equation because they're small. Yeah, it's a very subtle point. I go into a bit more detail in the notes about that, yeah. But it's important. Thanks for bringing that up. Right, so let me draw this. Right. So for those of you who know how this works, I'm not showing anything new or special. But for those of you who don't, all the drifts that I'm about to do all have to do with the fact that like the gyro radius for a given particle is v perp over that, which is like v perp over b, right? So anytime b changes, or anytime v perp changes, the Larmor radius of the gyro orbit of a particle is going to change. And so what's going on here, for an E cross B drift, you're going to see that this changes. And so this is going to modify the gyro orbit of a particle. In a grad B drift, this is going to change, and that's going to modify the gyro orbit of the particle. And because of these modifications, you'll get drifts. So let me show how this works. Let's see, what did I do? Right, so suppose I have, oh great, thank you. Suppose I've got some particle which is gyrating around the magnetic field. There's its guiding center position, and this Larmor vector is just sweeping around in a circle. Remember I just said that all the drifts that I'm about to talk about is either v perp is changed or b is changed. And b is not changing in this case, so I just assumed it was static. But this velocity is going to change because right here, it's going downhill. And right here, it's going uphill. Right? So it's going, the electric field is accelerating this particle this way. And over here, the electric field is decelerating the particle. So as this goes here, it's getting accelerated by the electric field. And so v is going up. If v goes up, the gyro radius has to go up. And so this particle comes around here. And now it's going uphill. So the velocity is going to go down because it's going against the electric field. And if the velocity goes back down, that means the gyro radius has to shrink. Right? So then it's going to start shrinking. And you're going to get motion that looks like this. And the speed at which this guiding center moves is that E cross B flow. So this is the velocity of the drift. And it's just because it's a finite Larmor radius effect in the sense that you have a particle which is executing Larmor motion, and as it samples the fields that it's moving through, it sees different things in different parts of its orbit. So, and then E cross B, yeah, so I didn't screw up. So E cross B is this way. If you did the same, I think I did this here for a proton, right? Because it was going around this way. If I did the same exact calculation for electron, I get the same thing. And the reason why is the electron will come down this way. For the proton, this was going uphill, but it's electron, so it's actually going downhill. Because the electric field, it's a negative charge, so it's going to speed up this way. And then it's going to do the same thing. It'll just, the handedness will be different, but the drift will be in the same direction, and it will be at the same speed. And it's this nice fortuitous cancellation of things that works out. You don't get that cancellation for the other drifts. And the way to see that is that I know that this force that I'm looking at is Q times E. And so I can just go down to this formula, and it looks like R dot is really just V parallel B plus some kind of force cross B So that's the general form, right? So guiding center motion is just motion along the field, and then any force any perpendicular force that the particle is subject to, you're going to get a drift. So the route from here is really straightforward. You just think, what other forces can I subject this particle to? Well, if it's massive, there's gravity. You just put mg right there, and you get a gravity cross B drift. So particles in the atmosphere do that. it's actually quite small because the other drifts are more important. So you can also think of a grab B drift that I'll show you in a second. If some particle's moving along a curved field line, it'll experience a centrifugal force because it's moving in a circle. Well, that's another force. You just put that in there and you get a curvature drift. So you just accumulate the forces that the particle is subject to, which are perpendicular to the field, and the particle is going to drift across the field lines because of that. And then just to come back to this question, a fluid element in MHD is comprised of particles. So just as all these particles F cross B drift, the fluid element will too. But the reason why the E cross B drift is so special is that it's species independent. It doesn't drive any currents or anything. All the particles just move together. The whole fluid element goes with it. That won't be true for the other drifts that we'll look at. Right, so in MHD, I wrote down this formula. Right, so that's Ohm's law in MHD, ideal MHD. Let's cross this formula with B. And what you'll get is this. So that's the same as this drift, right? So in the lab frame, the particles are drifting perpendicular to the magnetic field because of an electric field. That's a lab frame electric field. And what they're doing is they're drifting in such a way that the electric field in their frame is 0. So this is the electric field in the frame of a fluid element. This states that the fluid element moves with the E cross B velocity. This is saying that all the particles comprising that fluid element also drift with the E cross B velocity. So you have a whole fluid element full of particles, and they're all just drifting. They're not drifting in their reference frame. But the reference frame is drifting relative to the lab because of the E cross B drift. Yeah. And then back to your question. This is true in ideal MHD, right? In non-ideal MHD, there's a whole right-hand side here. And that corresponds to all the other drifts that I'm going to talk about. But all these are small. They're small by things like the wave number times the Larmor scale, which is tiny. And it's 0 formally in MHD. Things like K times skin depth, which is also 0 in MHD. So there's all these other drifts that I'm about to talk about, but they don't show up in ideal MHD, which has everything just E cross B drifting at the same speed. All right, so there's two ways to get the grab B drift. There's the proper way and the cheating way, and I'm going to cheat. The proper way was to get something that looked like this. I was taking d by dt. I was doing this, right? And the case I was looking at was this is constant and this is constant, so d by dt comes in here and hits v only. Now, suppose the magnetic field is not uniform. It's still time independent, but suppose it's just not uniform. Well, this d by dt, it's actually d by dt in the frame of the particle. And so that as the particle sweeps past things, it's going to see different magnetic fields. So what you could do is bring this d by dt inside, chain rule on the vector and also the magnetic field in here, and crunch and crunch. And that's sketched out in the notes. But there's something much, much simpler than that. And this just goes back to exploiting this formula and imagining what kind of forces there are on your particle. So when we got the E cross B drifts, you picture a point particle. It's subject to electric fields. You put that electric force in. To get the grab B drift, the way to think about it is go back to E&M class. And what does a particle doing this look like? It's a dipole, right? So you've got some field, and the particle's going around going around in a circle, and you're taught about the magnetic moment of this particle, which is like the current times the area, and the current has to do with QV cross B, which is the current running around this ring. And one of the other things you learn is that there's a force on a magnetic dipole, which is like that, right? It's a gradient of mu dot B. In this case, mu is just a constant. It's just a property of there's a particle moving around a circle, which looks just like a ring of charge. So there's a magnetic moment. So this is just mu, just this. And so here's a force. This is a force not really acting on the particle. It's acting on the guiding center, right? And you could take this force and you could plug it into the formula, and that's it. You're done. That's the grad B drift. So just to put that in into this formula over here. So I take a force, which is minus mu grad B. I cross it into B. I divide by mass and Larmor frequency. And this is a grad B drift. I didn't say what this mu is yet. This is magnetic moments of a particle. In magnetostatics and things like that, mu is just current times area. In this case, mu is that gives you this expression. So it's the perpendicular kinetic energy of the particle divided by B. I'll talk about this later, maybe in this lecture, about how this is a really, really important quantity because it's something called an adiabatic invariant in a magnetized plasma, which is really special. But just here, from here, if I just plug this in, let's see, this is QB on MC. The masses cancel. Mu is V perp M over 2B. Actually, let me just put that back. It's just like that. All right, so there's a few things that are special about this. One is that there's a gyro frequency here, so the charge matters. So the E cross B drift, all charges did the same thing. Here, electrons are going to do something different than the ions, which is good because this is actually giving you currents. Right? So this is something that contributes to the perpendicular current in MHD. You don't explicitly see this drift in MHD. It's not explicitly there. It's certainly not in the induction equation. It's been ordered out of the induction equation, so it's kind of hidden in that sense. But this is one of the things that giving you perpendicular currents in the plasma. The other thing is it's velocity dependent. So faster things drift differently than slower things. And that's not true with the E cross B drift either. So let me sketch out this grad B drift. So here's just the simplest possible setup. I have a magnetic field which is pointing out of the board, and it's got a gradient which is perpendicular to its direction. And suppose I'm a proton, and suppose this would be my orbit. Again, these drifts are finite Larmor radius effects, right? So you have to have a Larmor radius which will sweep over this gradient. Otherwise, you won't really see this gradient. That's one reason you don't see this drift in the induction equation MHD, because the Larmor radius is formally 0 in MHD. So if your Larmor scale is that big, you're not going to see this gradient. But if your Larmor scale is this big, you will see this gradient. So you'll have this particle that's coming over here. And remember, the gyro radius of all these particles is, remember I said you just have to change one of these, and then you get a drift. So what happens is this particle comes over here. It's not going to change its perpendicular velocity because magnetic fields don't do work. But it's sampling different regions of different field strengths. So over here it sees a weak field. If it sees a weak field, it has a large gyro radius. If you come over here, it starts to see a strong field. If B goes up, the gyro radius goes down. So then you end up getting motion that looks like this. Because you sweep over here, you see a stronger field, so then your orbit gets smaller. You come out here, you see a weaker field, so your orbit gets bigger. You come here, it's shorter again, so you bend around. And so you get a drift in this direction. And that's, that's B cross grab B direction, which is what we have over there. And you've got the math, but it's really easy to just do the pictures and figure out that the electron does the opposite. So this was a proton, so it's going this way. Electron's going to be going around, well, let's be realistic. It's a smaller orbit. And right, so it's going around that way. So it's coming over here. Well, I'll do it over here on this board. So it's going this way. So as it comes over here, it sees a weaker field. Wait, I'm screwing this up. There. Right. It's coming over here, it sees a weaker field, so it'll have a bigger Larmor radius, and then it'll see a smaller field, and it'll see a bigger one, and a smaller one, a bigger one, smaller one. So this is your electron. And it's grab-B drifting in the opposite direction. So again, there's a current which is set up here because of these drifts. So that's grab-B drift. I'm not going to go through all the drifts. I haven't said anything about if these particles are moving on top of a time variable field. There's something called a polarization drift that I'm not going to talk about. But they all have this form of some kind of force crossed with B. Like if you have a field line that's like this and a particle doing this, well, it's moving in a circle. And so there's a centrifugal force, which is the mass, its velocity along the field line squared divided by the radius of curvature of this field. That's the centrifugal force. And you just take it and you just sub it into the F cross B and you get another drift. So what's the radius of curvature of a field? It's just a measure of the gradients, how much the field direction, this B hat, turns as it moves along itself. So that's how these drifts work. You just find a perpendicular force and cross it with B, and then you just have to determine whether the ions or the electrons behave differently. Good. I'm going to skip ahead in the notes a bit. And let's see, this is 40. So any questions about this is just single particle motion. I mean, the nice thing about single particle motion is the cartoons always help. And you just ask, all right, what's the force at this point, 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 and it just tells you where to move. Okay, so moving on to kinetics. The way that kinetics is rigorously born is, all right, so this is one particle. And so let's just suppose we have a large number of particles. And we can describe those with the distribution function. Well, it just looks like this, right? So here's a distribution function. Sorry, this is not a force. This is a distribution function, say. I'm not calling it little f, which is probably what you're used to, because it's not what you're really used to. This is called a Kleeman-Towich distribution. And it just says if there's a particle at some location, it's 1. If there's a particle not at some other location, it's 0. So it's just a binary distribution. And you're just summing over all the particles. If you want to put things into different species, you just say, well, this is the distribution function for the ions. Say we sum over all the ions. All the ions are somewhere. And so this is either 0 or 1 at a given point, if there's a particle there or not. Well, sorry. And also, every particle has a velocity. So in the 6-dimensional phase space of all the positions and all the velocities, there might be a particle somewhere with some velocity. It's either 0 or 1. And we know how to evolve these. So this just F equals ma evolves v, and v evolves r, and we're done. Right? So this is it's not statistics yet. But you can, instead of writing down an equation for r and v, you can write down an equation for how this distribution evolves. Still, the problem, though, is that you have to evolve 10 to the huge number of particles. Or equivalently, in the Kleeman-Towich distribution, you have to evolve 6 times the number of particles that you have, dimensions. And that's just crazy, right? You're not going to do that. You can't do that. A computer can't do that. There's just not enough memory. There's another reason why you just shouldn't do that. One is that on a particle level, the system's very chaotic, in the sense that if I had 10 to the 20 particles and I took one of them and I ran that experiment and I ran an identical experiment, but I just took one of the particles and I shifted it by a small amount, you're going to get a microscopically different answer. Macroscopically, it probably looks the same, but microscopically, it's a different answer. And so that's not a very predictive thing. You want to ask, what is the likely evolution of the plasma, given that I don't want to say the exact evolution of the plasma, because number 1 is too hard, number 2, it doesn't mean anything, because it's sensitive to the initial conditions, and the initial conditions are fake anyway. Initial conditions are just something that physicists make up to solve ODEs. Right? So instead, what's done is that some kind of averaging is done over a probability distribution, which is called a Liouville distribution. I won't go into this. But this ultimately is what gives you a Vlasov equation. And I'll write this down and I'll say some words about it. So this is not Vlasov-Maxwell. So this is a Vlasov-Landau equation. This F is not this F. I'll say what it is. this equation, I didn't write this down, but without the brackets, this is completely deterministic. I mean, there is a particle somewhere, and it evolves to somewhere else, right? That's what this is. This is completely probabilistic, in the sense that this is the number of particles in some region of phase space. It's the likelihood that there is going to be a certain number of particles in a certain region of phase space. And so in going from here to something like this, with which you're probably more familiar, is that you're going from a deterministic description of the plasma. The particles move somewhere. There's a distribution function of these particles, which is this, and it changes accordingly, to something which says there's the likelihood of there being some number of particles in some interval of phase space, in some sort of region of space, region of velocity, and that probability evolves the same way like the wave function evolves in quantum mechanics. It's a probability which in this case characterizes your ignorance of the system. In quantum mechanics, there's an intrinsic uncertainty. Here, there's just a practical uncertainty, right? And you're evolving that practical uncertainty, which is this distribution function for species S. It evolves by these different pieces, which are kind of just self-explanatory. There's a Lorentz force. And then there's this right-hand side. And yeah, sorry.
So the uncertainty comes from our inability to track all the particles and their interposition.
Yeah. So there's a whole course at Princeton that I teach in the plasma program, which is you spend 3 weeks going from here to here. It's wrapped up in all sorts of questions of time reversibility. The first thing I wrote on the board at the start of this lecture was just F equals ma, which is time reversible.
Excuse me.
Yeah.
Dear listeners, can I ask you to ask questions a bit more louder?
Oh.
Because it was.
Yeah. Okay. Sure. I can repeat the question. It's fine.
But in next cases, just a bit more louder, please.
Yeah. Okay. What was the question?
Yes, I guess what I was referring to is like just our uncertainty.
Oh, you're right.
Deterministic.
Yeah.
From our inability to track all the particles and their initial conditions.
It's not just that. It's also that the initial conditions are somewhat arbitrary in the sense that even if there were a small change in the initial conditions, microscopically the system would evolve differently. So it's almost pointless to think about that. It's wrapped up into questions about reversibility and irreversibility and entropy increasing and what does it mean for entropy. And I'm not going to get into that. I could, if you want to learn, I can teach it to you. But yeah. So this right-hand side is a collision operator. Without it, this just means phase space is preserved. In other words, every single particle is somewhere, but like the probability of there being a particle somewhere is an invariant along a characteristic. It's like a Liouville theorem. But this right-hand side, basically all the uncertainty that came in this averaging procedure ends up on this right-hand side. And this is where particle interactions come, which screws up your notion of, well, if I had 10 to the 20 independent particles, that would actually be kind of easy to solve. But they're not. They're interacting through electromagnetic fields. And the chaos that induces into the problem is captured by this right-hand side. So I mentioned in the first lecture that you can get MHD and things like that just by taking a formula that's like this and taking moments of it. And what I mean by moments is that the number density of species S is just the velocity space integral of F, which is quite clear from this formula, right? So if I just integrate over d3v, the only thing that's left is the number of particles in a given region of space. There's also the momentum, which is just the first moment of F, and pressure tensor this is wrapped around, which is the second moment of F. So this is just characterizing, remember, so this is V minus U. U is the bulk velocity. It's what I meant in MHD. It's the fluid element velocity. So V minus U, it's the velocity of a particle minus the mean motion. So it's just the thermal motion. So that's why it's a pressure. So this is a thermal motion. This is a thermal motion. This gives you a pressure tensor. So you can derive equations for density, for momentum, for pressure tensor, and so on, just by taking successive moments of that equation. And MHD stops, ideal MHD stops here, by taking this and just making it an isotropic tensor, which just has a scalar sitting out front of it. And that's because if you assume that F is Maxwellian, you can do this integral. In general, you don't know what F is, so you have to evolve it. But if F's Maxwellian, this is just the Gaussian integral. You can do it by hand, and you just get n times t. So that's where MHD comes back in. OK, good. I go until 3:30, right? It's 2 to 3:30, 2 to 3:20. OK, 3:30. OK, good. So 40 minutes, good. OK, so I've just completely bastardized that, right? That's like the origin of kinetic theory in 5 minutes. There's a bit more in the notes about this, but not much. If you want to know more, I'd be happy to talk to you about it. What I'd like to move on to is the differences between a collisionless plasma and a collisional plasma. So you've seen MHD. That's a collisional plasma. It's Maxwellian to all orders because the mean free path is formally 0. But I also showed some examples of astrophysical systems like the solar wind, where the mean free path is the size of the system. And in that kind of environment, you get some collision-less effects. And I'm in Russia, so I have to talk about Landau damping. Right? This is Landau's house. So good. So you can look up Landau damping in a bunch of different textbooks. It's just a very standard thing now. You can find it in pretty much any plasma physics textbook. I'm not going to go through every detail. There's contour integration involved. Those details I actually did in the notes. So they're there if you want to learn about how to deform the contours and the contour integration, all this stuff. I'm going to lead you up to that point and then circumvent all that and just take all that stuff that I don't want to talk about and put it into a function called the plasma dispersion function, which is just a completely automated way of doing contour integration, and your computer knows how to do it. So the main reason that a collisionless kinetic system is different than a fluid is really this term right there. Meaning that suppose we just had a 1D plasma with no electric field and no magnetic field. This equation just says this. And what this physically means, I mean, you can think about this, and it's just a really simple PDE. You can solve it with method of characteristics. The solution to this is that F is constant on dx dt is V, right? So that's just method of characteristics for this PDE. So what this says is that there's a particle which is carrying around a piece of phase space with it. And what this is going to give you is something called phase mixing. And the idea is as follows. So here's my 2D coordinate system, just x and v. I know I've been using R. X is one of the components of R. And suppose I have here's some F, whatever that means. So here's some probability that there's some particles in this region of phase space. So how does this evolve? You don't even need the equation to know this. You know that velocity is bigger up here than it is down here. And so this thing is going to go here, and this thing is going to go there. And this is going to go kind of in between. And so the distribution function is going to change to look like this. And if you keep on going in time, this is just going to keep on wrapping up. And so if you take a cut at a given position in space, you just see finer and larger gradients in the v direction, right? So as this tilts, so the velocity gradient here wasn't so strong because it's broad. And then as you wrap this field through phase mixing, the gradient here gets sharper and sharper as this gets more and more distorted. You don't have this feature in a fluid. And the reason why is that the particles cannot free stream like this, right? A particle moves, and in a fluid, the mean free path is small, right? So a particle moves, it collides, it moves somewhere else, it collides somewhere else. There's no phase mix. The particles are not free streaming. They're just randomized. That's what a Maxwellian is randomized motions, right? So I want to look into the consequences of this for how the particles interact with the electric fields that they're producing. And that will give us something called Landau damping. This is where I need to take a data point. Who has seen the Landau damping calculation before? Good. Who's heard of Landau damping? OK. Do you want to hear about Landau damping? You're in Russia. The answer is yes. OK. So the simplest case of this is just electrostatic. So just forget the magnetic field. And just forget collisions. So this is called the Vlasov equation. When you forget the collisions, it's Vlasov. It's only Landau once you put the collisions in, because Landau derived the collision operator. So did Boltzmann, but that's for billiard balls, not plasma. So here's this Vlasov equation. It says that the probability that there's some particle somewhere with some velocity evolves because the particles move. And also because the particles, right, so the particles change their position because they're moving. And the particles change their velocity because they're subject to electric fields. So that's, in words, what this PDE says, right? Now, a plasma has both ions and electrons, so let's just append a little s here so that we're careful about what species we're talking about. And I can't solve this equation yet because I don't know what the electric field is. So I need another equation to close the system. And there's different ways to close the system. What Landau did was just use Poisson's equation. Right? So this is saying divergence of E is sum over species of the charges and the phase space. So this just gives you the total charge density is what's responsible for the divergence of electric field. I'm not going to use this because this is going to give all sorts of waves that I don't care about And in MHD, you don't care about. At large scales, you don't care about. If the Debye length is really, really small, you don't care about it. So I'm not going to use this. Instead, if I go to scales, which are really large compared to the Debye length, this equation just becomes that. So this is just, you sum up the charges, multiply by their number densities, it's just 0. So this is that quasi-neutrality I was talking about. So in any given region of space, there's approximately equal numbers of ions and electrons. And that's going to get rid of things called plasma oscillations that I don't care about in this lecture. And it'll allow us to focus on large-scale things. So I'm actually done. I don't actually have to know what the electric field is. Right? It is whatever it needs to be so that if I sum over all the charges, it'll be 0. So to get the electric field, I multiply this whole thing by Q, sum over charge, and I just integrate over the velocity space. And I just use that. And whatever the electric field is, that's what it has to be. Right. So the way that the Landau damping calculation goes, it's the same way that I talked about Alfvén waves and magnetosonic modes. You assume some background, and you stir it. So distribution function is just some background value. Might be a Maxwellian, doesn't have to be. And I'm going to add some delta F to it. So there's some disturbance in the force. Yeah, OK. I'm going to take this to be uniform, which means that there's no electric field in the background, because there's no pileup of charge or anything. And there's just some fluctuation in the electric field. It actually doesn't matter what it is, because it's going to be whatever it needs to be to ensure this. Right? And if you just plug this in, this is just uniform, time independent. That's your equation, just subbing in those things. Right? And so Cedric Villani, just got the Fields Medal for not dropping the right-hand side, but I'm not Cedric Villani. So I'm dropping the right-hand side. So you see it's nonlinear in the fluctuations. So you perturb the distribution function. That causes a perturbed electric field, and then that perturbed electric field feeds back on the perturbation. I don't need I'm perfectly fine with the job I have. I don't need a Fields Medal. So what remains is the Landau damping problem, which is just solving this linear equation. And you could do it a variety of ways. You could do it a wrong way and the right way. The right way is to specify initial conditions, or else you get it wrong. And that's what made Landau damping, is if you don't specify the initial conditions and do a Laplace transform, you get the wrong answer. So at t equals 0, there is some perturbation. Right, so I have a uniform plasma. I push on it at t equals 0. There's some disturbance. And this equation is going to modify that disturbance. Right? So it's going to modify it in two ways. One is that it's going to phase mix. Right? So these particles are going to carry that disturbance around and just mix it like that. The other thing is that that disturbance creates an electric field. And that electric field is going to modify the particles which were part of the equilibrium distribution. And what you're going to get is something called phase mixing, and then something called Landau damping. And in the full Landau solution, they're coupled together. You can't have one without the other. There's both phase mixing and an eigenmode response that comes from damping, which is this term. So I'm going to, in the interest of time, I'm just going to sketch out how this goes. So just like in the wave case, in the hydrodynamics or MHD case, I have a linear ODE of a fluctuating quantity sitting on top of a uniform background. And so I can just take plane wave solutions. Right? Another way of saying this is I'm just going to Fourier analyze this equation. And the nice thing about that is this gradient just becomes I times k. And I'm just going to, put a little hat on these to note that they're now Fourier amplitudes. They're not real space quantities anymore. So they're all k dependent. So that takes care of space. So I just solved space. That's 3 dimensions down. Remember, I'm just going to eliminate. I don't need to know what this is. I'm just going to eliminate it using quasi-neutrality. Now I've got 3 more dimensions in the velocity, and I have 1 in time. So to really get an exact solution, which is useful, I'll need to assume something about F naught. The standard thing is to just assume it's Maxwellian. You don't have to. We could do the whole calculation carrying around F naught with us. At the end, well, I'm going to do that, but at the end, I'm going to suppose F naught's Maxwellian. You don't have to. So the only thing left is really determining how to invert this time operator. And the way to do that is a Laplace transform. So what you do is you write, something like that for the Fourier space. And then for the Laplace transform, so there's just a standard Laplace transform. This omega is a complex quantity. It includes both waves and damping of waves and things like that. And it's the same thing as the Fourier transform, just in a complex, in the other complex direction. And the point is to just be able to replace this d by dt with just a number and turn this equation into an algebraic equation. So what that happens is you get just minus I omega there. And the other part of this that comes out is that initial condition. So now this is just algebraic, right? So this is a number. This is a number. I'm going to get rid of this term, so I don't need to know what it is. And this is just a number. And I can solve for delta f just fine. The trick then is to get back into real space, because right now, if I solve for delta f, that delta f is a function of omega and k. So it says, if I have a certain wavelength in my plasma, which oscillates and damps with a certain complex frequency, this is how delta f evolves. But that's not measurable. I mean, without some work. You go back to the real space. And so that means we're going to have to do an inverse Laplace transform, and that's where Landau magic happens. That Landau magic is in the notes. I'm not going to go through it. But I am going to say why you need it. And why you need it is, again, this is easy to solve now. It's algebraic. I want to solve for delta f. I just divide through. So that's delta f. I'm done. Right? Now, I have to eliminate this delta E, but I told you how to do that. I just multiplied this by Q, sum over charges, integrated over velocity space, and that term has to be 0. That's just quasi-neutrality. And that'll tell me what delta E is. So right now, I'm just going to leave this here as just a number, but you can actually sort it out. The trouble here is that when I do an inverse Laplace transform, you see those poles in my integral. So there's spaces where this integral goes crazy because omega is k dot v. And the reason why I didn't erase this right-hand board is, what's the solution to this? Whoops. It's just this. In this 1D problem, it's just scalar k, right? And you see this, just look at the Laplace transform there. It's omega, and this is k dot v. So this pole has something to do with this phase mixing. And so, like I said, I'm not going to go through the procedure, but this L, there's a Laplace contour. You have to deform it because there's a pole here. And how you deform that is Landau genius, and it's done in the notes. I'm going to write down the final answer after you do it. I really tried to do it out in detail in the notes, so it's everything's there. All right, you get 2 pieces. Let me check the time. Okay. And they're both something that you can understand physically. First, I'll just start with this piece. So this was my initial condition. There was some disturbance in the plasma. And we now know that this is associated with phase mixing. So there's some initial condition, and then from that initial condition, the particles just start streaming. And they carry this initial condition out with them through phase space. And that's just what this does, right? This just oscillates it in velocity space. It just requires this sharp structure in velocity space, which is oscillatory, which is what I drew on this board earlier. There's another piece. These CJ are just numbers. They just come from a residue when you do a Cauchy theorem, so don't worry about them. The point is that this had something to do with the structure of F naught. And that thing is phase mixed too. So what these 2 things are saying is there's an initial condition. And from that initial condition, the particles just free streamed. That's what this is. There was a response, which is that delta E, that electric field. That response is also phase mixed. So all the stuff just gets phase mixed by particles free streaming. And then there's a second piece, which is not free streaming. And this is the eigenmode response. This is if you don't solve the initial value problem. And what this is going to tell you, it's not clear. If you've never seen this before, you don't understand what this is. I'm just writing it here as a place marker. Right? So this is stuff, initial conditions and a response that get phase mixed. And then this response, which is just an eigenmode response of the plasma. There's some natural frequencies in the plasma, and they're going to actually damp. And that damping is in here. So now I'm just going to close by actually telling you the physics that's in this problem. And there's a nice visual of phase mixing in the notes to check out. Right, so here's the solution. This solution is valid if these omega j's right here satisfy a certain dispersion relation. if F naught is a Maxwellian, you can write down that dispersion relation in closed form. And I'll write that down now. Okay, so there's this prefactor here. You see that the right-hand side 0, so it doesn't actually matter that I put a 4 pi here or that I put a k squared here. There's reason that I put it there. You can read about it in the notes. But there's charge squared of the species, the number density of that background that I perturbed, the temperature of that background that I perturbed, and then there's this funny thing. So 1 plus the zeta, which is that complex frequency divided by k divided by the V thermal. So this is 2. It's the thermal speed of species S. And this thing, which is called the plasma dispersion function. And this is what sort of industrializes what Landau did. Right? You can look this up. I have notes about it in the notes. It's also in something called the NRL plasma formulary, which you can get online. You can't write down, it's an integral that you can't do analytically. You can do it in closed form analytically in certain cases. And I'm just going to mention one case, which is going to help you with some of the stuff that Lev's going to do. So what I'm doing right now is actually analytically something that you're going to do with a PIC code later. So the idea here is that we solve for the response, provided that this omega, all those, the sum, well, yeah, I should have said something first. This thing, this plasma dispersion function has an infinite number of roots. So like usually a dispersion, like when we did dispersion relations earlier for MHD, there was 2 alphane waves, one going this way and this way. And there were 4 magnetosonic modes, 2 going this way, 2 going this way. This has an infinite number of solutions. And that's why there's a sum over here. This is a sum of all the omega solutions which satisfy that equation. So how do you get the ones that you want? So we're going to do that really quick. Suppose I had just an ion electron plasma. So and let's just make it hydrogen, so Z, the charge of the ion is 1. You know. So that means that this is 4 pi E squared N naught I, K squared T naught I, 1 plus this for the ions. And we do the same thing for the electrons. So that's just the dispersion relation written out for the ions and the electrons. And it turns out that even though, so the Z function, I'll write down what it looks like. It's just this. It's a Gaussian. That's the easy part. And that also explains the root pi here. But then there's a pole. So you can't solve this in closed form. But it's clear that if this zeta is small or big, you could probably get some approximate solution. I mean, if it's really big, you just have to integrate a Gaussian. You know, if it's really small, you could just Taylor expand this. And then you have a Gaussian integrals, right? So in certain limits, you can actually write down a closed form solution for this integral. And that's exactly what we'll do. So it just starts with a really simple, yeah, sorry?
Excuse me. Could you repeat, because I feel I don't understand the last passage.
Yep.
Could you repeat how does the, let's say, the general equation on the left side comes from?
Yeah.
Because, okay, you get there, I understood.
Right.
Okay, but
Yeah, I kind of skipped, I mean, yeah. So, right, so the question is, I mean, I just wrote that down, it was magic. Right?
yeah.
That was the question. Where, what, okay. Right, so at some point in the solution, the same way, right, so when we did the MHD waves, right, there was linear algebra that gave you a matrix times a vector, and then you just set the determinant of the matrix to 0, and that's your dispersion relation, which would give you something like that. In the kinetic case, it's something very similar. It's just that instead of having a matrix, you have an integral to do. I mean, this is spelled out in the notes. I'm trying to think the most compact way of saying this. Right, so in the waves case, we say these equations have solutions if the determinant of this matrix is 0. In this case, this solution exists if there's a relationship between these omegas and these k's. And that's that condition. So this is a validity condition on this solution. Like the omegas and the k's have to be related by that. So, you know, I'll wrap this up. Well, Sasha's not here, so I could just keep on talking. Good. So the way to make progress with this is, so which species has the higher thermal speed, electrons or ions? It's the electrons, right? Their mass is tiny. So if they both had comparable temperatures, the electrons have a larger thermal speed. 5, there he is. Okay. So what we could do over here is, remember I said I can solve this. I can write down this thing in a closed form if this zeta is either small or large. I could just Taylor expand either way. So let's suppose that things are such that omega over k is in some interval, right? So suppose it's slow compared to the electron thermal speed, but it's that phase speed is fast compared to the ion thermal speed. That means zeta I is big, but zeta E is small. And then you can go Taylor expanding this or whatever and just get closed form solutions. And I'll just write down the answer that you get and close with some physical discussion. Then there's about 100 pages after that about kinetics in a magnetized plasma that I won't talk about. But I'll revisit that in the third lecture. Good. So if you do that, you just assume those things. We can check if that's true at the end of the calculation. Let's just assume those things and expand that z function. You can look up online. You can find, I also have it in the notes, what kind of closed form expressions the z function takes in different limits. So it's very well known. Your computers actually know it as part of the complex air function, which is in your computer. So if you do that expansion to this, you get the following. You get a wave whose real frequency is just, a wave number times something that looks like a thermal speed. So it's a sound wave. So this is something called an ion acoustic wave. It's what a sound wave looks like in a collisionless plasma, where the electric field's important. It depends on the electron temperature, but you see there's ion mass. You can also get the imaginary part. And it looks like this. And so this is the Landau damping. So you see there's an imaginary part to this frequency. It's negative. That corresponds to damping. And then there's this factor that has to do with electron temperatures or ion temperatures. And then you can go back to this assumption where we said omega over k is smaller than this and much bigger than this. And you can see from here, omega over k is square root of ti over mi. For that to be bigger than V thermal I, the electron temperature needs to be large. So the only validity constraint here to get this closed form expression is just that the ions are cold. So physically, what's going on? Right. So we put in a sound wave. It decays exponentially at some rate. And in MHD, it does not do this. You know, sound waves you put in MHD, linear sound waves will just happily go forever. They'll steepen and shock eventually, but not linear waves. They'll just go. Here we put a linear sound wave into the plasma. It exponentially decays. And the reason is as follows. There are two problems of different difficulty in the homework that I gave you. One is, well, they're both concern Landau damping that you can take a look at. The issue is that you've got these particles which are free streaming. And I ascribed some significance to this kind of thing, right? This was in the pole. And this is what made the problem difficult. It corresponds to free streaming, things like this. For a given wave vector and a frequency, there's some special particles. Those special particles are moving with the phase velocity of the wave, right? So there's a wave right here. It's moving along. You know, there's omega versus k. So there's a speed to this wave, omega over k. And there's certain particles in the distribution function whose velocities are tuned just right so that they can move with the wave. It's kind of like the classic example you see in textbooks is that there's surfers. The surfers who are really slow aren't going to catch any waves. The ones that are really fast aren't going to catch any waves. But if their speed is just right, they can ride the crest of a wave, right? So in this case, that wave is an electrostatic field, and there's charged particles which are riding it. And if those waves are riding the field, they can either give energy to the field or they can take energy away from the field. So in the classic surfer, the surfer takes energy away from the wave because he's riding it. But you can also have situations where maybe a surfer is so powerful that he's swimming so fast and strong that he can actually push waves, right? That wouldn't be very productive from the standpoint of surfing, but that can happen. The reason why you get damping is that in a Maxwellian, there are more surfers than pushers. So the idea is that if I have a distribution function that looks like this, which is a Maxwellian, here's the characteristic velocity of my wave, my ion acoustic wave. And I'm going to look at potential surfers, things that are close to that phase speed. There are more particles that are going slightly slower than that wave than there are particles that are going slightly faster. So there are more particles that have the ability to be sped up by the wave pushing on them because they're going slow. So they'll get resonantly pushed, and that'll speed things up. And so that's how you get damping. So what's happening is that there's electrostatic response from this initial condition. Some of these particles are tuned just right so they can ride that wave. and they just leach energy out of the electric field. And that causes the electric fluctuation to decay. So you can work through this in the problem sets in two different ways. One is a neat way involving Hermite transforms, which is kind of cool. That's kind of difficult one. Another way is a calculation due to Lifshitz and Pityevsky, another Russian thing, where they calculate this kind of resonant phenomenon on a single particle instead of a distribution function, which is a really cute calculation. So I'll close there. I'll only say that if you glance through my notes, there's a bunch between this and lecture 3. And that's basically doing everything I did just here for a magnetized plasma. So a plasma where the gyro radius of the particles is very, very small. And that changes things. Because particles can go along fields, but they have a hard time going across fields. And that changes things a lot. Like, you can't free stream across the field. You try to free stream across the field, and you just start going like that. So anyway, thank you. Enjoy. Bye. It is a lot if it's the first time you've seen this. But I do encourage you. I mean, there's a reason why all the details in the notes, right? You should go back and work through it yourselves. Or maybe you just understood everything. Yeah.
So in the PDF, none of the particles actually have exactly that velocity, right? You said there's some region around.
Yeah.
How wide?
How wide? Yeah, it depends on. So there's this kind of resonance. And something I kind of swept under is that suppose you have a little bit of collisions. This thing, when you actually solve this problem rigorously mathematically, there's an I epsilon here. And it defines sort of the window of these resonances. You could take that window to be infinitesimally small. You get the same answer. But in a plasma with some collisions, that collision frequency will give you something about that width. Something I didn't mention, which is related to that, is run through this whole thing in your mind about surfers if I have a bump. And that's unstable.